Welcome to our deep dive on light.
Oh, yeah.
We're using excerpts from the Book of Light by J. Christopher Weslan to uncover light's journey from its,
Yeah.
birth in the Big Bang
Yeah.
to its role in shaping life and human understanding.
It really is amazing how often we just take light for granted, isn't it?
Yeah.
But it's so central
Yeah.
to everything,
So
from
right.
the universe's first moments to the technology we use today,
Yeah, absolutely.
everywhere.
Well, let's start with the Big Bang then.
Okay.
I mean, it's wild to think about the universe beginning in darkness, right?
Yeah.
So how did the very first light emerge from
Mm.
that cosmic explosion?
Well, picture this. An incredibly dense point, right? Packed with all the universe's energy and matter, and suddenly, boom, it explodes.
The Big Bang.
Right. But in those first tiny fractions of a second, the universe was just a scorching hot, opaque soup of particles.
Oh.
I mean, light, as we know it, couldn't even exist yet.
So if those early moments were lightless, how did we get from that darkness
Yeah.
to the brilliance we see today?
So as the universe expanded, right,
Mhm.
and it cooled, a really remarkable separation happened.
Uh-huh.
Imagine, like, two powerful forces just intertwined since the very beginning,
Yeah.
starting to disentangle.
Okay.
And that's basically what happened with electromagnetism
Okay.
and the weak nuclear force
Right.
and this cosmic uncoupling.
Yeah.
That's what gave rise to those very first photons.
So the very first light in the universe wasn't even starlight.
Right.
It was this cosmic glow
Exactly.
from fundamental forces separating.
Yeah, I mean, isn't that mind-blowing?
It is, totally.
What if they...
What happened to those early photons?
Yeah.
Did they just bounce around?
Well, not exactly.
Oh.
As the universe kept cooling, right?
Uh-huh.
Those early photons were interacting with all sorts of particles.
Like quarks and stuff?
Yeah, quarks, all that. But eventually, things cooled down enough for stable hydrogen atoms to form.
Okay.
And that was a pivotal moment.
Gotcha.
About 380,000 years after the Big Bang, the universe, which had been this dense fog,
Yeah.
became transparent.
Wow.
Light could finally travel freely.
So what happened to the light from that era, though? Can we still see it?
That's it's still out there.
Really?
But its journey over billions of years has stretched its wavelength.
Uh-huh.
So it's shifted into the microwave part of the electromagnetic spectrum.
Okay.
So what was once this brilliant cosmic glow,
Yeah.
it's now just this faint whisper.
We call it.
We call it the cosmic microwave background radiation.
Wow, so we can actually still detect that primordial light?
We can?
That's incredible.
It's amazing.
So how did we go from this diffuse cosmic glow
Yeah.
to, the brilliant stars?
Well, the emergence of stars marked a whole new chapter
Uh-huh.
in the story of light, you see, as
Yeah.
gravity pulled matter together. It created these immense pressure and heat.
Yeah.
And that ignited nuclear fusion
Oh,
within these stellar furnaces.
So these like giant nuclear reactors?
Exactly. And with that, the universe was bathed in starlight once more.
And of course that brings us to our own sun.
Yes, our sun, a star born about 4.6 billion years ago,
Wow.
bathes our planet in the light that sustains life as we know it.
And that takes us to another chapter.
It does.
The intertwined story of life and light on Earth.
Absolutely.
So early life faced some serious challenges, right?
Oh, yeah.
I mean, intense ultraviolet radiation from the sun
Yeah.
must have been a constant threat.
It was a huge threat.
So how did those early life forms cope?
Well, imagine those early life forms, right?
Uh-huh.
These simple organisms just residing in the oceans.
Yeah.
UV radiation was a big danger to them.
Right.
How did they cope with this constant bombardment of energy?
Did they just like hunker down and hope for the best?
Well, some did.
Really?
They retreated to the depths during the day
Oh,
to escape the sun's harshest rays, and they'd emerge only at night.
interesting.
This behavior actually led to the development of what we call circadian rhythms,
Oh, wow.
the internal clocks that govern our daily cycles.
That's so cool.
And it's in so many organisms,
Yeah.
including us.
That's a pretty clever way to avoid,
It is.
getting fried by the sun.
Yeah.
But eventually, life found ways to actually use light, right?
Exactly.
Right.
Over time, life on Earth didn't just hide from light,
Uh,
it learned to harness it.
wow.
The evolution of photosynthesis was a complete game changer.
Yeah.
Plants developed this amazing ability to capture sunlight
Right.
and convert it into energy.
Photosynthesis,
Exact.
fueling their growth and releasing oxygen
Yo-
into the atmosphere.
Transforming the planet.
Wow.
and paving the way for more complex life.
And those more complex life forms,
Yes.
they needed ways to sense and navigate, right?
Absolutely.
This increasingly intricate world.
And that's where the eye comes in.
The eye.
The evolution of the eye was another pivotal moment
Mm.
in this dance between life and light.
Yeah.
Now, organisms could see.
Okay.
They could find food, avoid predators, and just explore in ways they never could before.
It's like this, like an arms race.
It is. It's an evolutionary arms race.
Yeah.
The better you can see, the better your chances of survival.
Exactly. Yeah. Sharper vision would give you such an edge
Totally.
in a world full of,
Right.
predators and prey.
Yeah,
Did this arms race, did this play a role in human vision?
absolutely. This evolutionary pressure ultimately led to primates.
Okay.
And then eventually to early humans.
Uh-huh.
Our ancestors, with their forward-facing eyes, they gain stereoscopic vision.
Oh, right.
That ability to perceive depth,
Yeah.
crucial for hunting, gathering, and navigating a 3D world.
It's amazing to think about, like, our ability to see, right? Appreciate a sunset or,
Right.
gaze at a star-filled sky. It all goes back to those survival instincts.
It does.
But our fascination with light goes way beyond just survival.
It does.
We've always been drawn to its like power and mystery, right?
I think so.
And one of the earliest expressions of that was mastering fire.
Absolutely. A pivotal moment in human history.
Yeah.
A technological leap that changed our relationship with light.
And with the world around us.
Exactly.
Fire. Now that's a game changer. Talk about harnessing power of light and heat.
It wasn't just light and warmth.
Right.
It was a revolutionary technology.
Yeah.
Protection from predators, cooking food, extending our activities into the night, even fostered social interaction.
People gathering around,
Exactly.
flickering flames for warmth and storytelling.
It's amazing.
Yeah, it's fascinating to think about how we went from just using fire opportunistically to actually controlling it.
Right.
How did we make that leap?
It was gradual,
Okay.
driven by observation and experimentation. Early humans likely observed how wildfires could cook food,
Right.
drive away animals.
And they maybe even, tried cooking on hot spots.
Maybe so.
From natural fires.
Could be.
Then there was this ability to maintain it for longer periods.
Right, which led to more permanent settlements.
Yeah, with fire as a central point.
I think so.
And then finally, friction methods.
Oh yeah, a real breakthrough.
Yeah, creating fire on demand.
Giving us unprecedented control over this powerful force.
That control led to some serious advancements too, right? Our ability to work, socialize, right?
Well, it's so coincidence that a lot of anthropologists believe that mastering fire coincided with rapid brain development.
Interesting.
Those extended daylight hours
Right.
provided by fire, more time for learning, tool making, social interaction.
All that contributing to our cognitive evolution.
Exactly.
So fire, a source of light and heat,
Yeah.
played this crucial role in shaping who we are today.
It did.
It's like this symbolic link between our past and our modern world. But what about the efficiency of light production over time?
Well,
We've come a long way from campfires, right?
we have. The economist William Nordhaus actually did some fascinating research on this.
Really?
He analyzed data going back millions of years,
Wow.
even to the time of early hominids.
That's a long time.
It is, to track the efficiency of light production.
Okay.
And what he found was that for a really long time, progress was incredibly slow.
I mean, for thousands of years.
Yeah, we relied on fire, torches, simple oil lamps.
Right, right.
But after 1800,
Yeah.
things started to accelerate dramatically.
Industrial Revolution.
Exactly. We went from candles and oil lamps to kerosene, gas lighting, then incandescent bulbs.
And now LEDs.
Right. And other incredibly efficient lighting technologies.
It's amazing how far we've come.
It is, in such a short period.
It's like this hunger for light, It's ingrained in us.
Yeah.
A legacy from those early ancestors huddled around those flickering flames
I think so.
for warmth and protection.
I agree.
But light's always been more than just a practical thing, right?
Yes.
It's also a source of wonder,
Absolutely.
inspiration,
Yeah,
even spiritual significance.
that's a great point.
And that brings us to another fascinating aspect of our relationship with light.
Yeah.
Its role in shaping our understanding of the universe.
Okay.
I mean, especially in ancient empires, religion and observations of the night sky were very much intertwined.
Absolutely.
Right.
Ancient civilizations looked to the heavens for guidance, for answers, for a sense of order.
Right, in a world that often felt really chaotic and unpredictable.
It
They
did.
saw the stars as, like, divine entities.
Yeah.
They mapped out constellations.
It did.
They created elaborate cosmologies.
Trying to explain the movements of the celestial bodies.
And those cosmologies weren't just spiritual, were they?
No. They serve really practical purposes.
Yeah.
I mean, they used these celestial observations to predict seasons.
Agriculture.
Yeah, for agriculture, for navigating vast distances.
Right.
And even to maintain social order.
Within their empires.
Yeah.
So the priests and astronomers, these were like the early scientists.
They were.
They were trying to make sense of the universe using whatever tools they had.
And the knowledge available.
Right.
It was fascinating.
Observing these cycles of the sun and moon and stars, I mean, that would lead to awe and wonder.
Of course.
It's like this giant clockwork unfolding above us.
It's beautiful.
Some of the greatest thinkers in ancient Greece were captivated by this.
Yeah, Socrates, I mean, his statement that humans have to rise above the earth to truly understand the world.
Yeah, or Plato's belief that the sky leads us to another realm.
And Anaxagoras, who said that the investigation of the sun and moon and the heavens was the very purpose of life.
And then Ptolemy.
Oh, yeah.
His beautiful observation, when I trace at my pleasure the windings to and fro of the heavenly bodies, he said, I no longer touch earth with my feet.
Beautiful.
It's clear that this allure of the heavens, it's captivated us for a long time.
A very long time.
Driving us to seek answers, in the stars.
I agree.
And this fascination, this desire to understand the universe.
Yeah.
The nature of light itself, I mean, it's led to some incredible discoveries.
They have.
Scientific breakthroughs.
It has.
And that brings us to another chapter in our story.
Okay.
The history of scientific theories about light.
Right.
A journey from those ancient Greek concepts of light as rays to the mind-bending world of modern quantum mechanics.
Yeah, you ready?
Absolutely. Let's illuminate the path and see where it takes us.
Yeah, let's go.
To the development of eyes and the mastery of fire. But now let's dig into how humans have tried to really figure out what light actually is. Where do we even begin with that?
Well, I think our journey has to start with the ancient Greeks.
Okay.
I mean, they were really the pioneers in systematically investigating the natural world.
Yeah.
And light was no exception to that.
Makes sense.
They were some of the first to really try to tackle the question of what light is and how it behaves.
So what were some of those early ideas about light? Did they have any theories that kind of stood the test of time?
Well, one concept that has really endured from the Greeks is the idea of light traveling in straight lines.
Okay.
Like rays.
Like beams.
Yeah, beams emanating from a source. Thinkers like Pythagoras and Epicurus, they imagined these rays either coming from the eye or from the object being seen. And while we now understand vision differently, this idea of light rays, it really laid the groundwork for what we call geometrical optics.
Geometrical optics, that sounds kind of familiar. Is that what we use to understand how lenses and mirrors work?
Exactly. You got it. Yeah. Euclid and Ptolemy, two brilliant Greek mathematicians, they use these ray diagrams to explain reflection and refraction.
Refraction, that's when light bends, right?
Yes, exactly.
When it goes from like air to water.
Exactly. They showed how light bends when it passes from one medium to another.
Okay.
And you know what? These principles are still used today.
Really?
To design eyeglasses, telescopes, all sorts of optical instruments.
Wow, so the Greeks really gave us this powerful tool for understanding how light interacts with stuff and travels through different materials.
Yeah, they did.
Did they ever figure out what light actually is?
That question, proved to be a real challenge. They debated whether light was like a stream of tiny particles or some type of wave, but it was the Arab scholars, building on the work of the Greeks, who really took our understanding of optics even further.
I'm curious to learn more about their contributions.
Yeah.
Were there any standout figures?
One name really stands above the rest, Ibn al-Haytham.
Ibn al-Haytham, okay.
A brilliant scholar from the 11th century. He conducted all these really meticulous experiments.
Okay.
And he made groundbreaking discoveries about light and vision.
What kind of experiments did he do?
Well, he carefully studied the human eye,
Okay.
and he realized that we see objects because light bounces off of them and enters our eyes.
Okay.
He even built a device called a camera obscura.
What's that?
It's essentially a pinhole camera
Okay.
to demonstrate this principle.
Interesting.
He also made significant contributions to understanding refraction, rainbows,
Rainbows, yeah.
and even eclipses.
Wow, he was really ahead of his time.
He was.
It seems like we're getting closer to understanding light, but this debate about whether it's a wave or a particle still seems to be going on.
Yeah, that debate continued for centuries.
Mm-hmm.
And in the 17th century, two real giants of science,
Uh-huh.
Christian Huygens and Isaac Newton,
Oh, wow, Newton, like
Yeah.
the gravity guy.
the one and only.
He had opinions about light, too.
Oh, yeah.
What did he think?
He favored the particle view of light.
Okay.
He argued that light travels in those straight lines,
Yeah.
casts sharp shadows,
Uh-huh.
and reflects kind of like tiny particles bouncing off a surface.
Okay.
He even called these particles corpuscles.
Corpuscles, okay.
And, his corpuscular theory of light, it seemed to explain a lot of the things that people were observing back then.
That makes sense. So Newton had his corpuscles. What about Huygens?
Well, Huygens, he proposed something totally different.
Okay.
He envisioned light as waves.
Waves?
Yeah, kind of like water waves or sound waves.
Okay.
He argued that light's ability to bend around corners,
Mhm.
which we call diffraction, it could only be explained if light was a wave.
So instead of these like little bullets of light,
Yeah.
we've got these waves, rippling through space.
I know, it's a beautiful image.
It is, isn't it?
But if light is a wave,
Yeah.
what's it waving in?
That was the big question that stumped scientists for centuries.
I bet.
Huygens. He proposed that light waves traveled through this mysterious substance called ether.
Ether.
It was supposed to permeate all of space.
Like an invisible ocean?
Yes, exactly. An invisible ocean that light waves traveled through.
That's a pretty wild thought. So now we have this battle of the titans. Huygens with his waves and Newton with his particles.
Yeah.
Who was right?
Well, this is where the story gets really interesting.
Okay.
It turns out that both of them were partially right.
Wait, what?
Light actually has a dual nature.
It behaves as both a wave and a particle.
Both. How is that even
I-
possible?
I know. It's one of the most mind-bending concepts in physics. We call it wave-particle duality.
My brain just did a backflip.
It's definitely counterintuitive,
Yeah.
but that's the quantum world for you.
Okay.
At the subatomic level, things don't always follow the rules that we're used to in our everyday experience.
Right. But before we go down the quantum rabbit hole,
Yeah,
let's stick with the wave theory for a bit.
sure.
What evidence was there to support that?
One of the most convincing pieces of evidence came from a really famous experiment
Okay.
done by Thomas Young back in 1801.
Okay.
It's called the double slit experiment.
Okay, I've heard of that.
He shined a beam of light through two narrow slits,
Okay.
and then he looked at the pattern that was created on a screen behind the slits.
Right.
And you know what? Instead of two bright spots like you might expect,
Yeah.
he saw a whole series of alternating bright and dark bands.
What caused that?
Those bands, you see, they're a classic sign of wave interference.
Interference.
Yeah, imagine like dropping two pebbles into a pond.
Okay. Yeah.
The ripples from each pebble,
Uh-huh.
they'll spread out
Yeah.
and eventually they'll overlap.
Right.
And you get these areas where the waves either reinforce each other.
Making them bigger.
Exactly.
Okay.
And that's the bright bands.
Gotcha.
And then you have areas where they cancel each other out.
And those are the dark bands.
Exactly.
So Young's experiment was kind of like the light equivalent of dropping pebbles in a pond.
Exactly. And the pattern he saw
Yeah.
could only be explained if light was behaving like a wave.
Okay.
Spreading out, interfering with itself.
Right.
This experiment was a big win for the wave theory.
So the double slit experiment, it showed pretty clearly that light can act like a wave, but what about that ether that Huygens was talking about?
Ah, yes, the ether.
Did scientists ever actually find it?
Well, that's where things took another interesting turn. In the late 19th century,
Mm-hmm.
two American physicists, Albert Michelson and Edward Morley,
Okay.
they designed this really brilliant experiment
Yeah.
to try to detect this elusive ether.
How did they do that?
Well, they reasoned that if the Earth was moving through this invisible ether,
Right.
there should be what you could call an ether wind
Okay.
that would affect the speed of light.
So they were basically trying to measure the speed of light in different directions
You got it.
to see if it changed depending on this ether wind.
Exactly. It was a really clever idea.
It was, yeah.
But the results of their experiment were totally unexpected.
Really?
They found absolutely no evidence of any ether wind.
And no ether wind, so what did that mean?
Well, it was a huge blow to the ether theory. I mean, if light was a wave, it had to have something to wave in.
Right, it can't just wave in nothing.
Exactly. But the Michelson-Morley experiment really suggested that this ether just didn't exist.
So where did that leave physicists? Back to square one.
Not quite. You see, even though the ether theory was basically dead, the wave theory still had some fight left in it.
Okay.
And the person who really breathed new life into it was James Clerk Maxwell.
Maxwell, didn't he work with electricity and magnetism?
He did. That's what makes his work so incredible.
Okay.
He developed this set of really elegant equations that unified electricity, magnetism, and light.
All together.
Yes, all under this one grand theory of electromagnetism.
Wow. So how did that help us understand light?
Well, his equations predicted the existence of what we call electromagnetic waves.
Okay.
These are disturbances in electric and magnetic fields that propagate through space.
At a certain speed.
At a very specific speed.
And that speed is?
The speed of light.
So what you're saying is Maxwell showed that light itself is an electromagnetic wave?
Exactly.
It's not a mechanical wave traveling through some invisible ether.
You got it. It was a huge triumph, his theory.
Yeah.
I mean, unifying three fundamental forces of nature and revolutionizing our understanding of light.
That's huge.
It was. But, the story doesn't end there.
Of course not.
Just when the wave theory seemed to be pretty much settled, a whole new set of discoveries would come along.
Okay, I'm sensing another plot twist.
And challenge our understanding of light once again.
So is this where the particle theory comes back?
It does, but with a twist.
Okay, I'm intrigued.
This time, it wouldn't be Newton's corpuscles. Instead, it would be the idea of light as tiny packages of energy called quanta. And this, my friend, is where we enter the world of quantum mechanics.
Quantum mechanics, now that's where things get really interesting. How did this idea of light quanta come about? Okay, so we're on the edge of this quantum revolution.
We are.
Like a huge change in how we understand light in the universe. This whole idea of light, quantum,
Right.
these little packets of energy. It's very different from those waves we've been talking about. So where did this idea come from?
Well, the seeds of this revolution were sown in 1900 by a German physicist named Max Planck.
Max Planck.
He was wrestling with this problem called black body radiation.
Oh, black body radiation.
Which describes how objects emit light when they're heated.
Okay, so heated objects emitting light. I mean,
Yeah.
that sounds pretty straightforward. What was the problem?
So classical physics,
Yeah.
it predicted that as an object got hotter,
Yeah.
it should emit more and more intense radiation
Okay.
across all wavelengths.
Uh-huh.
And eventually, it would reach infinite energy.
Infinite energy. That doesn't sound right.
It didn't. And clearly, that wasn't happening in reality.
Right, right.
Something was off.
So the theory and the experiments weren't matching up.
They weren't.
What did Planck do about it?
Well, he came up with a radical solution.
Okay.
He proposed that the energy of light wasn't continuous,
Okay.
but instead it was quantized, meaning it could only exist in these discrete packets, like little bundles of energy, which he called quanta.
So not just any value.
Yeah.
It's like steps.
Exactly. Think of it like a staircase. You can only step on the stairs,
Right.
not in between them.
Not in between.
And similarly, light energy could only take on specific discrete values.
Okay, so instead of like a ramp, it's more like stairs.
Yeah, a series of distinct steps.
Each step being a quantum of energy.
Exactly. It was a bold idea,
Yeah.
a big departure from classical physics.
But it worked.
It did. It explained that black body radiation spectrum perfectly.
And yet Planck himself wasn't totally convinced by it.
It's funny. Sometimes even the most groundbreaking discoveries
Sure.
are met with skepticism.
Even by the people who made them.
Yeah. He saw it more as a mathematical trick
Okay.
than a real description of reality.
But Planck's idea, it didn't stay in the shadows for long, did it?
It did not. Enter Albert Einstein,
Einstein.
a young patent clerk at the time. Who would take Planck's idea and really run with it?
That's the relativity guy, right?
The one and only.
What did he have to do with light quanta.
Well, Einstein was this fearless thinker,
Yeah,
always willing to challenge the status quo.
right.
And in 1905,
Uh-huh.
he took Planck's quantum hypothesis
Yeah.
and used it to explain something called the photoelectric effect.
Oh, the photoelectric effect. That's about shining light on metal
Yep.
and getting electrons to pop out.
That's the one.
So scientists had noticed that shining light on certain metals would cause these electrons to be emitted.
Yes.
But they couldn't figure out why it only happened with certain frequencies of light.
Right. Not just any light.
So there was like a frequency threshold
There was.
below a certain frequency.
Yeah.
It didn't matter how bright the light was.
Yeah.
You wouldn't get any electrons.
Nope.
But above that threshold, even if the light was really faint,
Yeah.
you would get electrons.
You would. It was strange.
That's weird.
And classical physics, it just couldn't explain it.
So what did Einstein do?
Well, he drew on Planck's idea
Okay.
of these light quanta
Uh-huh.
and came up with a brilliant explanation.
Okay.
He suggested that light isn't just a wave, but it also exists as these tiny packets of energy,
Yeah.
which he called photons.
Photons. Okay.
There's little bundles of light energy that we now know are fundamental particles.
Right, right.
And he proposed that each photon,
Yeah.
it carries a very specific amount of energy
Okay.
proportional to its frequency.
Okay.
So when a photon hits an electron in the metal,
Mm-hmm.
it can transfer all of its energy to that electron.
Okay.
And if the photon has enough energy, meaning if its frequency is high enough,
Yeah.
it can knock the electron loose, causing it to be emitted from the metal.
So it's like each photon is like a tiny bullet.
It is. It's a great analogy.
And if it hits the electron hard enough, it can knock it free.
Exactly. And the higher the frequency of the light,
Yeah.
the more energetic those photon bullets are.
Yeah. That makes sense.
And this beautifully explained why the photoelectric effect only worked with certain frequencies of light.
That's really cool.
Einstein's work was huge.
Yeah.
It didn't just solidify this concept of light quanta.
Right.
It also showed that light could act as both a wave and a particle.
So we're back to that duality thing.
We are. It depends on the situation.
How did people react to that?
Well, it took a while for scientists to wrap their heads around this new way of thinking about light.
It's such a strange idea.
It is, and reality itself, but the evidence kept piling up.
Right.
Experiment after experiment confirmed this dual nature of light, and eventually it became one of the cornerstones of quantum mechanics.
It's amazing that something as basic as light could lead to such a huge shift in how we understand the universe.
It is.
But let's step back from the quantum stuff for a second.
Sure.
So we've talked about how light can act as a wave or a particle. But how is light even created in the first place?
To understand that, we have to go back to the atom. Remember those electrons
Yeah.
orbiting the nucleus at different energy levels?
Right, like planets around a sun.
Exactly. So when an electron absorbs energy,
Yeah.
it jumps to a higher energy level, a larger orbit.
Okay.
But it can't stay there forever.
Right.
Eventually, it falls back down to a lower energy level.
Like a ball rolling down a hill.
Exactly.
Okay.
And when it does that,
Yeah.
it releases that extra energy.
Right, but how does that turn into light?
Here's the key.
Yeah.
That energy is released in the form of a photon.
A photon. Okay.
So when an electron goes from a higher energy level to a lower one,
Yeah.
it emits a photon with a specific energy, and that means a specific frequency or color.
So every time we see light
Yeah.
from a light bulb or a star
Yeah.
or even a firefly,
Yeah,
we're seeing these tiny quantum jumps happening inside atoms.
exactly. Think about like a neon sign.
All right.
The electricity flowing through the sign excites the neon gas atoms,
Mm-hmm.
causing their electrons to jump up to higher energy levels. And when those electrons fall back down,
Yeah.
they release photons, creating that bright, colorful glow.
So the color of the light depends on the specific energy difference between the electrons' orbits.
That's right.
And each element has its own unique set of energy levels,
It does.
which is why different elements emit different colors when they're excited.
Exactly.
That applies to all kinds of light sources, right?
It does.
Just like from fluorescent lights to
Okay.
stars.
It's all about those tiny quantum leaps,
Yeah.
those transitions between energy levels within atoms.
It's amazing how these quantum things give rise to the light and color we see every day.
It is. It really makes you appreciate those connections between the microscopic and the macroscopic.
But atoms aren't the only way to create light, right?
You're right. There are other pathways to create photons.
Like what?
Well, take incandescence, for example.
Incandescence.
Like, imagine a horseshoe
Okay.
being heated in a blacksmith's forge.
All right.
As it gets hotter, it
Yeah.
starts to glow. First red, then orange, then yellow, and finally white hot.
And that's because the heat is causing the atoms to vibrate more and more.
Exactly.
And those vibrating atoms emit light,
Across a range of frequencies.
which we see as different colors.
You got it. The hotter the object,
Yeah.
the wider the range of colors it emits.
And incandescent light bulbs,
Yes, same principle,
the electric current heats the filament.
causing it to glow white hot.
But those are pretty inefficient, aren't they?
They are. They waste a lot of energy as heat.
Which is why we've moved to things like fluorescent bulbs and LEDs.
Right. Those are much more
And
efficient.
those use different methods, right?
They do?
They're not heating a filament.
Oh, no.
So fluorescent bulbs,
Yeah.
they use gas discharge.
To excite mercury atoms,
Okay.
which emit ultraviolet light,
Uh-huh.
which is then absorbed by a phosphor coating
Okay.
inside the bulb, which re-emits it as visible light.
And LEDs, they're semiconductors, right?
They are...
They can emit light when you run an electric current through them.
Exactly.
It's amazing how understanding light has let us develop all these different lighting technologies.
It is. We've come a long way from those flickering flames.
To LEDs.
It's amazing.
And we can't forget about bioluminescence.
Ah, yes, bioluminescence.
Living organisms that create their own light.
One of nature's most spectacular displays.
It really is. Fireflies, glowworms, deep sea fish.
Even some fungi.
Wow.
It's amazing.
But how do they do it, though?
It's all about chemistry.
Chemistry, okay.
Bioluminescence is a form of chemiluminescence,
Okay.
where light is produced through a chemical reaction.
Gotcha.
And in most bioluminescent organisms,
Yeah.
it involves a molecule called luciferin
Luciferin.
and an enzyme called luciferase.
Luciferase, what do those do?
Well, think of luciferin as the fuel
Okay.
and luciferase as the stark.
Right.
That ignites the reaction.
Okay.
So when luciferin reacts with oxygen
Uh-huh.
in the presence of luciferase,
Yeah.
it releases energy in the form of light.
So it's like a controlled burn.
It is a great way to put it.
But instead of heat, you get light.
Exactly. And the different colors we see,
Yeah.
from the firefly's yellow-green glow to the anglerfish's blue light,
Uh-huh.
those are due to variations in the luciferin molecule and the surrounding environment.
Bioluminescence is just such a cool reminder
It is.
of how diverse and ingenious life on Earth is.
It shows us how light isn't just something we observe, you know?
Yeah.
Something that life itself can create.
And manipulate.
Exactly.
Well, we've covered a lot of ground today.
We have.
From the Big Bang to the evolution of eyes to, the mastery of fire and the nature of light itself.
Yeah, light's been this fundamental force
It has.
in our universe, a source of wonder and a real driver of scientific discovery.
So what are some of the key takeaways you hope our listener will take away from this?
Well, I hope they'll come away with a deeper appreciation for the role that light plays
Yeah.
in our universe and in our lives.
I mean, it's not just something that illuminates our world. It's a fundamental force that shapes, everything from
it's
galaxies.
the behavior of atoms.
Absolutely.
Yeah.
And I also hope they gain a sense of awe
Yeah.
at the beauty and complexity of light.
I agree.
From rainbows to the stars.
It's incredible. There's still so much to discover about this fundamental aspect of reality.
And that's the beauty of science, isn't it?
It is.
It's a never-ending journey of exploration and discovery.
It is.
We've come a long way in understanding light.
We have.
But there's still mysteries out there.
There are.
New things to uncover, new ways to use its power
Absolutely.
for the benefit of humanity.
Well said.
Well, as we wrap up
Yeah.
this deep dive, I want to leave our listener with a final thought. We've seen how light can be both a wave and a particle.
Right.
These contradictory concepts that coexist beautifully. But what if that duality
Yeah.
is a reflection of something deeper?
Like what?
Like, what if the universe itself is more interconnected, more complex than we realize?
Yeah.
A place where boundaries blur and opposites merge.
That's a really thought-provoking idea.
It suggests there's always more to learn, more to explore, and more to discover,
There is.
both in the world around us and within ourselves.
I like that.
So to our listener, keep looking up at the stars,
Yes.
keep marveling at the beauty of a sunset, and never stop questioning the nature of light
It's fascinating.
and the wonders it reveals about our universe.
Well said.
And until our next deep dive, keep exploring.